This is a neat quote that I found from T.S. Eliot if we're going to talk about information.
Were the two lines adjacent to each other, or they're two separate quotes?
No, that's one quote. My talk today is going to be on information, and I'm going to talk to you about the Markov group, something that's of special interest to me. It's going to be in 3 parts. 4 parts. Background. I have to tell you a little bit about Markov processes. Then I'm going to talk about network metrics. And then I'm going to talk about logical and numerical uncertainty. And then we're going to look at a few applications to quantum mechanics at the very end, but this will be relatively short, and hope that that will just leave some open questions that will stimulate your mind. The real question that I want to ask here is information. We're in the information age, but what is information, and how do we understand what it is? And my proposal today is going to be somewhat radical. I really want to tell you that I believe the Markov group of transformations is of incredible importance, and it's been overlooked. I would even venture to say that in the end, the Markov group could be as important as the rotation group or some of the other groups that we use in physics that we swear by. In particular, the reason that I say that is because the Markov group deals with diffusion and therefore entropy, and therefore approach to disorder, and therefore the era of time. And we're really familiar with diffusion and entropy from classical systems, as this entropy constantly increases and disorder increases irreversibly, something we don't see in our time reversal quantum theory. It even defines our direction of time. So things that we're interested in that have to do with the direction of time and how that's defined and irreversibility are somehow or another connected with diffusion, entropy, information, and the Markov processes. This really began for me in my interest in information theory and entropy and diffusion when I was able to show that the general linear group in n dimensions over the reals, that's all linear transformations that are not singular, that can be evolved continuously, just like the rotation group. I published that in 1985 in the Journal of Mathematical Physics, and that was really my first interest. I then got off on doing other things, but in that first work, I need to talk to you about 10 minutes about that to give you some background. What I was able to show was that the general linear group in n dimensions can be broken up into 2 groups, a Markov type transformation where you continuously unfold a Markov transformation, and an abelian scaling transformation, which just makes the axes larger or smaller by some measure. This Markov group is defined by leaving the sum of all of the components of a vector invariant. In other words, x1 plus x2 plus x3 up to xn. If I leave the sum of those components invariant, not the sums of the squares, not the vector times its complex conjugate, but the sum of those, as you would with probabilities, then that defines what we mean by the Markov group in n dimensions. However, we normally want to interpret that as having to do with probabilities. And so we then want to say we can decompose that into those transformations that preserve the positive definiteness of the components and those that do not. And when we have to do that, we lose the inverse. And when we lose the inverse, then we end up with what is called a Markov monoid. The Markov monoid is a Markov transformation. It's a group, but where you've removed the inverse. So you no longer have an inverse and you no longer really have a group. And that is formally called a monoid. Now, the thing that I'm going to really be talking about today, one of the 2 core things, is that I have found that the Markov monoids are isomorphic to all the networks that exist. That means if you give me a network, it's 1-to-1 with a Markov monoid, and vice versa. In other words, with a generator. And the Markov monoids contain diffusion, entropy, and irreversibility. So somehow or another networks are tied in with these. In addition to that, I'm going to use these Markov monoids in a totally separate venture to look at how we could define a new type of mathematics that allows us to have logical and numerical uncertainty. The first object of what I was trying to do was to find continuous Markov transformations, in other words, a Markov-type Lie group. And of course, the Markov transformations are not a group per se, but we studied the group that contained them and then restricted to the allowable Markov transformations. These form the Markov monoids. If we want to understand diffusion and irreversible processes, we need to go back 100 years. But before I do that, I have a little chart here. If I showed you this first, then you probably would have left. But this...
Turn on the light, please. That small light.
Yeah.
Okay.
This right here, you can imagine as all of the general linear transformations that are not singular. And you can divide it up into two parts, what I call the scaling transformations. That just means make this axis 10 times as long or 1/3 as long. And the rest of the transformations are the Markov transformations. That's the Markov Lie group that leaves invariant the sum of the elements of a row, of a column, of a vector. Those are divided up into those transformations that are called the Markov monoid that also maintains the positive definiteness, and the inverses. We throw the inverses away because they take us to negative probabilities, and this is where we get irreversibility and diffusion, like the dies cast. And so you can't reverse that because you have to throw these out, they become non-physical transformations. So now we are concentrating on these transformations here, this Markov monoid, and we can show that every graph is one-to-one with one of these Lie group generators, and also that this can be used to generate these transformations only if this parameter alpha is positive, and that's where we stay with the Markov monoid. All of these here conserve the sum of the elements. So it's just to let you think about it a little bit graphically. If we go back some time and think, where did this start? Then we think of 1905 of Einstein's work on diffusion theory. And a year later, 1906, was Markov's work. And Markov matrices have been used ever since then, are very heavily used in the social sciences, and give us a diffusion. For example, if you want to look at population that's changing, and you know the probability to move from New York to California and the probability to move from Nevada to South Carolina, and you have all these cross probabilities, and you start with any population, then that is a Markov transformation that conserves the number of people and tells you how your population is going to evolve. That is an example of a Markov transformation. Why? Because you're conserving the total number of people that are in the United States. It turns out that that other group over there, the scaling group, allows you to have a birth rate and a death rate all at the same time. So if you add those transformations in, so you take the ones on the far right, the ones on the far left, the abelian scaling group, then you can have birth and death at the same time with those transformations. I want to give you an example. If we use Bryan-Kett notation, we're thinking of transforming a vector into a new vector using this Markov transformation. And here's an example of one that we can see right here. In this one, what I did was I said it's 80% probable to stay put and 10% probable to move to two adjacent cells. And I connected the system back around to itself. And you can see that if I start out with all of my occupation in any one place, like right here, that after the transformation occurs one, I'm 80% likely to be in the same place, or I have 80% of the substance in the same place. 10% is moved one up, and 10% is moved one down. And if I apply it again, that happens again, then it happens again. And what has been done in the past is people have done the Markov transformations sequentially. And what we're doing here is we're looking at them as a continuous unfolding, an exponential unfolding, as in the sense of the groups.
Joe, is this transformation, do you say it is reversible or irreversible? Like
Yeah, it's reversible. This is irreversible if you're going to maintain positive definiteness. You see, you can reverse the transformation, but when you do, you have some transformations that take you to negative probabilities. And that is the whole point of why, when you make that restriction, you end up with irreversible systems. And that's what gives us our error of time. So we want to conserve the sum of the elements of this vector. And the way that I originally came up with these generators was trying to think of a way to do this that would work. And the solution is to rob Peter to pay Paul. For example, if I take 10% of one person's money that they have with them and give it to another person, and 5% of the second person's money and give it to the first person, I can do that transformation on a continuous basis and never run into negative probabilities. So we can say, what is that infinitesimal transformation? And that infinitesimal transformation is given by these two elements at the bottom. My graphics kind of comes in kind of slowly. And so these are the infinitesimal generators of robbing Peter to pay Paul and robbing Paul to pay Peter. And if we take these two elements and look at their commutators, we notice that they close. This is a very interesting Lie algebra because it turns out to be the smallest Lie algebra that exists. It's smaller than, for example, Jx, Jy, and Jz. And you don't notice it if you do the normal decomposition of Lie groups and Lie algebras because this is not semi-simple. It's not anything. It has no Casimir operators. It's a very interesting Lie algebra. And you also can show that this is isomorphic to an algebra that if you just take commutator of A and B and make it equal to A, then that's the same algebra as you have here. So this algebra is the two-dimensional version. This thing exists in any number of dimensions. And this is actually the smallest Lie algebra. And now what we're going to do is we're going to exponentiate that. And when we exponentiate it, this is all we do. We take the algebra here. We take it to e to the power some parameter like s times, this should be an s right here. And this gives us our Markov transformation. And this is what we get if we unfold that. For those of you who haven't tried doing that, I wrote this out on the thing here. And it's really very straightforward for those graduate students that haven't had this before. You simply take the matrix and use the definition of the exponential 1 plus s times lambda, s times l plus s squared over 2 factorial l squared, and use matrix theory. This 1 here is to symbolize a 1 and a 1 on the diagonal. And you take this matrix and you multiply it out. You find they have the interesting property that L squared is equal to minus L. Once you know that, you know what L cubed is equal to, and so forth. And you can see that the series that you get here, it's very easy to see that it gives you 1 minus e to the minus s and e to the minus s. Now, if you're going to require that this is always non-negative as s evolves, then you have to take s positive, and that's where you get the irreducibility. Anyway, I thought I would actually write that out. And you can see that you do get a transformation that is Markov. The sum of the first column is 1, the sum of the second column is 1. You can do that in higher dimensions. I wrote out one here in 5 dimensions. You just put a 1 in any off-diagonal position and a minus 1 on the diagonal, so that the sum is 0. And therefore you have n squared minus n independent such objects, and they will always close and form a Lie algebra, and they will always generate Markov transformations of that dimensionality. You might say, graphically, is there a way to see this and what's happening? The answer is yes. In 2 dimensions, it's very easy. You're conserving x plus y, not x squared plus y squared, which would be moving around in a circle like the rotation group. But you're conserving x plus y, which means you're moving along a straight line. You'd say, that's the translation group. It's not the translation group. In fact, what you do with that transformation over there is you're mapping this line back into itself using linear transformations, but you've separated out with the monoid those transformations that take you from a positive definite sector from here to here in the positive quadrant. You're mapping those back into the positive quadrant again. And that's what this particular Lie algebra does. It takes you from the positive quadrant back into the positive quadrant. If you allow your Lie parameters out front, the s's, when I go to many dimensions, here I just have an S1 and an S2 for those two operators L. But in higher dimensions, you have a whole bunch of s's. Every one of those has to be exactly positive. And then you get exactly the Markov transformations. And what you're doing there is you're actually moving around on a hyperplane that's perpendicular to the vector 1, 1, 1, 1, 1. So if you imagine the hyperplane in n dimensions, that's perpendicular to 1, 1, 1, and you look at the positive hyperquadrant, these transformations, the Markov monoid, is moving you around in a non-translational way among those and preserving probabilities, preserving the positive definites, but it gives you diffusion, and it's irreversible. And that transformation I showed you over there a minute ago shows you why that's true. Those components are interpreted as probabilities, then you have non-negative values. That removes the inverse transformations. So allowable transformations are those and only those with non-negative linear combinations of your basis elements. And this removes the inverse in all of your transformations. And this is what gives us a Lie monoid, as it's called. If we add that scaling group in, you say, what is that scaling group? The scaling group has a 1 in one place on the diagonal and a 0 everywhere else. So it ends up giving you just a 1 right here. And so you're multiplying this. And now here, in this circumstance, S can be positive or negative. So it just multiplies you by a factor. And this is what, in that population model, would give you birth rates and death rates. It would say your population exponentially grows or exponentially decays in a particular state while you're doing all these simultaneous population movements. Our conclusion on Lie monoids is that one is able to utilize now the power of Lie groups and Lie algebras to study Markov processes. So what we've really done, what I did, and this is 20 years old now, is to say we've got Lie groups and Lie algebras here, and we've got Markov processes over here. We've now merged those two branches of mathematics. So it lets us use the power of one and the power of the other. If I look at Dirac-Broncat notation, you can actually say that this vector 1, 1, 1, 1, 1 multiplied on the left by the Markov transformation leaves that invariant. And that's really what you're meaning, saying you transform the hyperplane into itself. Finally, by adding those scaling transformations, you get all the possible continuous linear transformations. Here's another quote I especially like. So this is the first part on the background. I want to talk about networks now and how we can apply that to the concept of networks. And this is actually due to Georgia O'Keeffe. I really like it. It really, of course, is you can get your own meaning from it, and you can also read, so I don't need to read it to you. But I particularly like it. It means we need to abstract from things, and that's kind of what we do with these networks and with this other information. I want to tell you that networks are important and ubiquitous. We really don't run into them much in physics. So we don't, in all of my career, I never really thought about networks that much until I became involved in looking at the work that I was doing with DARPA on trying to look at internet security. Networks embody some very difficult and unsolved mathematical problems. In fact, one can say that there's a whole class of problems in mathematics that involves networks where things are totally unsolved. For example, did you know that if we look at two of these matrices that classify networks, we can't even tell from that if the two networks are the same or not. We have to permute, look at every possible permutation to see if they're actually coincident. In other words, there's no way to distill the set of numbers down that represents a network to very quickly see if two networks are the same, if the topologies are the same. It turns out you'd say, well, can we use the eigenvalues of these matrices? And the answer is no. It turns out that you have a problem of graph isometry, where if I have two networks, they can have exactly the same eigenvalue structure and yet be topologically different. It's just very strange. And a network, you might say, what is a network? What are we thinking about here? It's a set of points. Some of these are joined by lines. And these lines may or may not have certain values. They may be just ones and zeros. I connect two people or I don't connect them. They know each other or they don't know each other. Or I could connect them with lines and say, this is like a social network, and I connect all of us by how well we know each other. Do we know our pets' names, our dogs' and cats' names? Do we remember their phone number? So we could have a weight as to how well we're acquainted with another person. And that again, is another type of network or graph. You'll notice then that if I'm going to connect people with this connection matrix, I only need the off-diagonal elements, and that's critical because I'm connecting I to J. I'm connecting person 32 to person 12, and I'm not connecting a person to themselves. That has no meaning. So the diagonal of the connection matrix is not defined. So any matrix that has off-diagonal, non-negative numbers, including 0, is a possible topology for a graph or a network. Here's an example of one such graph. I've got Cij there that says, for example, the interpretation here is that node 1, 2, 3, 4 and 1, 2, 3, 4, they're always square. Number 1 is connected to 4. It's connected to 2 with a strength of 4. It's connected to node 3 with a strength of 2, and it's not connected over here. And this is precisely the graph that I drew up here between nodes 1, 2, 3, and 4. 1 is connected to 2 with a strength of 4, and it's connected both ways. It's symmetric. But you'll notice that 2 is connected to 3 with a strength of 1, but 3 is not connected back. It's an asymmetrical type of connection. 2 knows who 3 is, but 3 doesn't know who 2 is. That's one way to think of it. And so it's asymmetrical. And the investigations that we're doing now into internet traffic says it's a big difference. If we have one computer that's broadcasting out to many other computers, those computers may not respond. That may be on a type of attack. So the asymmetry in the connection matrix may be important for recognizing attacks between computers if we use a large internet system. So that gives us an example of the matrix, and you notice I've left the diagonals out there. If we think of why networks are important or why they're so ubiquitous, then we can look at some of the networks that exist. We certainly have the internet. We've got phone networks. We have mail, UPS. We have air traffic. What would that be? Well, if you think of all of the airports in the United States, and you say, what is the connection? The connection is if there is a United flight or if there's not, or we could say, if we could look at the number of passengers transported on the average each month, or the number of flights each month. So there are many ways to define the networks, but we could define it with air traffic, or with highway traffic, or waterways, or railroads, pipelines. We could look at financial networks. We could look at money that flows between two accounts. If you stop and think about it mathematically, this is a different kind of animal. This says, here's an account here, 1, 2, 3, 4, 5. Here's another account, 6, 7, 8, 9. And money is passed back and forth between these different accounts. It is always the state of the system is described by a matrix, not by a vector. And that's really the thing that sets it apart from the things we study in physics. Because when we study physics, if you think about classical mechanics, you think about throwing a baseball. Okay, the ball's moving in three-dimensional space, so it's described by a vector. You say, well, I want to use phase space, so I want to look at its velocity and its position both, so I'm in a six-dimensional space with a baseball. And that's still a vector. You say, well, I want to look at Avogadro's number. I want to look at a gas. It's just a bigger phase space. It's still a vector in this phase space. So we're dealing with the motion of a vector. If we look at quantum mechanics, we're looking at the motion of a vector. It's in the Hilbert space. It's huge. It may have enormous indexing, but we're still looking at the state of the system as described by a vector. Here we're looking at the state of a system that's actually described by a matrix. Electric power grids, electric circuits and devices, computers, the inside of one computer or the connection of an entire set of computers. Natural gas distribution, and so forth. We have biological, neural networks, our brains, our lymph system, our blood system. We even have disease systems. If we take hundreds of thousands of nodes, or hundreds or thousands, then there are billions of connections between them. And if you think about the internet, these are changing every second. And so the problem is you're looking at trillions of numbers flowing in. This is a rate of data flow that's overwhelming. It looks like Christmas tree lights. And what we would like to know is, it's kind of like a situation with gas molecules. We want to know what is happening in general without seeing the details. It doesn't do us any good to know that this molecule right here in thermodynamics is moving with this velocity, and this one over here is moving with this. They change, and then somebody else takes over, and they go fast, and this one goes slow. What we want to know is, what's the pressure? What's the temperature? What is the state of the system? And so what we want to do is seek some kind of network metrics, just a few variables or functions of all of these that represent the entire network. This is similar to the roles that thermodynamical variables like temperature fulfill for gases. the problems. On networks, there's no concept of distance. On the internet, I'm just as close to Hong Kong or New York as I am to the people down the hall. So I can't, without a concept of distance, define a pressure or a volume. There's no concept of energy, so we can't really define temperature or heat or internal energy. There's no obvious probability distribution. We have a connection matrix, but it's not a probability distribution. We can artificially make one, but it's somewhat artificial. So we really can't define entropy or information metrics associated with the order or disorder. Yeah?
I can't agree that there is no distance in the network.
There are ways to define distance. You can define it as the number of links. People have done that. So there are artificial ways to do this, but in the natural sense, like we think of a metric space, the distance between here and Hong Kong is not very important. But we could look at a discrete number of links that it takes to get somewhere. But then that changes on the internet, because how far am I from you? If I send an email, it may go to New York and then come back to you through 20 transactions, or it may just jump down the hall, depending on the service. So that constantly changes. So, I would say I would question the utility of it. When I speak of these realizations, these are things that I came up with that would help me think about how these networks could be thought of. Since the connection matrix is exactly and totally defined by off-diagonal, non-negative real numbers, then each connection matrix is exactly isomorphic to one of these elements of the Lie monoid. That's incredible. All we have to do to make that match perfect is to adjust for our connection matrix, take for the connection matrix, and I don't really have one much up here, take for the connection matrix the negatives of the sums of the remaining elements in that column. So if I look at a column in the connection matrix, they're all positive numbers, the diagonal is not defined, I now take the sum over the entire column, make that number negative, put it in the diagonal, and then I have an exact generator for a Markov transformation. So it's in that Markov monoid. And that gives us, we use that freedom of the diagonals of C.
Can I ask a question?
Yeah.
If it's isomorphic, you could do this, you should do this in both ways.
You can do it both ways. Each one of those exactly defines a network.
In this case, your statement is that each matrix represents different network.
It does.
And each Markov process, could you prove this?
Yes. Yeah, can we look at it later?
Okay.
Yeah, if you think about it, if you have a different set of numbers that are off-diagonal, then it's the off-diagonal numbers that define the monoid. It's also the off-diagonal numbers that define the matrix, the network.
There could be different network for the same.
They're the same network. I mean, if I have one monoid, I get one transformation, and vice versa. But maybe there's something I missed. We'll discuss it later. So every possible graph or network topology generates one unique Markov transformation, and conversely. So if you give me a connection matrix, if I write out this connection matrix C, fix the diagonals, exponentiate it, then I will always get a Markov transformation. One that's realistic. In other words, it doesn't violate probability. Since any Markov transformation consists of columns which sum to unity, then they can be considered as probability distributions. So this is the next realization. And now that we have a probability distribution, we can compute an entropy on it. We could use Shannon entropy, we could use any of the Rene entropies, because once you have a probability distribution, you can say, what is the order and disorder associated with that probability? That will give us an entropy measure, or an information if we think of the negative of entropy for that. Networks are generally asymmetric, and the weights that are away from a node are not necessarily the same as the weights toward a node. What I transmit out is not the same as what I transmit back. Therefore, this asymmetry is important. And I can do the same thing in constructing a transformation that's a Markov transformation. It works on row vectors rather than column vectors. And I can get another set of entropes, and that set of entropes in that case of asymmetry is different from the first set. So now I have a pair of metric values for every node. one for the row and one for the column for any given connection matrix. So what I've done is I have reduced n squared minus n independent values down to 2n values. We don't really care which node is doing what. That's the next thing. Just like we don't care which molecule is moving with what speed. So what we can do is we can sort all of these nodes in order by, say, column entropy. And when we sort them in order, then of course we get a non-decreasing curve. So we get what I call a spectral function that represents all of the different entropies that we have. The theory there is that if I look at that spectral function, somebody is connecting to this many with this order and with these weights. Somebody else is connecting here. If that pattern is about the same, then we might say that the order and disorder associated with that topology is about the same. So we could, in some sense, say the distillation into the entropy functions of that network hasn't changed much. In other words, if things were okay before on your internet, they're probably okay now. If they were the same before in your airline network or your power grid or your social network or your criminal network, they're about the same now, if the curve has not changed much. Now you want to track that curve over time and say, what is normal behavior or distribution for the curve and what is abnormal? We can sort the rows in the same way that we sorted the columns, and that gives us an almost unique way to look at a row spectra at the same time. Thus, for each window of time that we can capture a network image, like every minute on the internet or every second or whatever, for banking transactions, you might capture it once a day or once a month. Then you can recompute the spectra and see if it's about the same for the row and the column spectras or whether they have changed. Realization 5 is that spectral form could be studied by many means to see if it deviates. You could just take an R squared with the normal distribution or the mean distribution of that function and then end up with one number, how well it correlates with the normal. And that would give you one number R squared for the rows, one number R squared for the columns. That reduces the entire network at a given time to a correlation coefficient with the normal state of the network. One can also use wavelet theory and other types of decompositions that we're familiar with in physics to look at how much this has changed or how much this has not changed. We don't know whether this, how well this algorithm will actually work. We're in the process of looking at it for internet traffic, applying it to different kinds of networks. We have a provisional patent applied for. And for earlier work, Dr. Goodkoff and I filed a patent based upon a different method using mutual entropies and generalized Rene entropy. And then we have still another patent that we applied for that was a provisional patent with many of you know Dr. Shmuel Nuzanov. Conclusion is we can represent a network at a given instant by a pair of spectral curves. The metrics can be shown to have an interpretation of the entropy rates of the dispersion of a conserved fluid on that network. It's kind of interesting. And so actually, in that framework, you can understand what the eigenvalues and eigenvectors are of this transformation. They're like the normal nodes of an oscillating system where the combinations are exponentially decreasing, because remember, this is a dispersion, this is a diffusion process, and everything approaches equilibrium. So you can show that there's one eigenvalue that's 1, and that's maximal, and everything else is less for these systems. And therefore, everything decays and goes to 0, except for one stable pattern for that particular type of Markov transformation. I'm pretty much on time. This is another quote. I like quotes. Because they always say something important if I fail to say anything important. This is from Turing. He did this, I think, in about 1952, which was pretty insightful considering the state of computers back then. Most people didn't even know what a computer was. They thought it was some machine that could think. And the reason that I put this quote up here is because what I'm going to talk about with logical and numerical uncertainty is going to pertain in the end to some rather interesting things that I think are exciting about how we deal with computers. I think you start out as a scientist worrying about things. Something bothers you. And everybody else seems happy with it, but it bothers you more than other people. And if you're not bothered by anything, then you kind of have to go home or let somebody else tell you what to work on. And I've always been troubled with the fact that our real number system is really, I think, inappropriate in a way, because real numbers are never used to measure things. We say that the length of this room is a real number, but everyone in here knows that the width of this room is not represented by a real number. If we tried to measure a real number, we'd have infinite amounts of information. It would take us infinite time. We would be forever looking down in the quantum domain. First of all, the sheetrock isn't that uniform. And next, we have quantum fluctuations. Then we try to look at the positions more than that. We'd be creating virtual walls like pair creation. And so we know that it's absolutely impossible to measure things exactly. And yet we still use the real number system. And we say, well, we round it off. It's just the substructure that we deal with, and we can throw the extra digits away. But since no one has ever really measured a real number, it would require infinite effort and infinite information. Our ways of combining these numbers that are truncated or cut off is not on good mathematical foundation. If you look back at the first of our physics books, and one of the things that always should bothers me is this is just a set of ad hoc rules where you do this, and you throw away these digits and you round them off. Where's the mathematical theory that underlies that? And that's really not there, to the best of my understanding. So this is not going to be your regular talk. I mean, I'm making a radical suggestion for you. I contend that the real numbers are actually inappropriate for physical measurements. And I'm going to provide, by saying that, I'm going to provide you with a substitute, otherwise I wouldn't do it. And I contend that they should be replaced by a mathematical system that exhibits and tracks the associated uncertainties and tracks that through the entire process of our mathematical operations and does it in a well-defined way. Such a system would have to be built on a physical measurement process rather than the Russell and Whitehead type of thing. As you're aware, I'm glad Pavel isn't here. There's no way I could get through the next sentence or two. May not with some of y'all. But Boole, of course, built Boolean logic about the 1920s, and then after the 1920s, we have Russell and Whitehead's foundational work around the turn of the century, again around 1900, where they built a logical structure of arithmetic, which sounds kind of trite, but it really isn't. They built their structure. The mathematicians went on to look at the Dedekind cuts and other ways of using real analysis to define the real numbers and the complex numbers and the rationals. But in all of that, you're using pure logic. You're not thinking as a physicist would think. You're not thinking, what do I measure when I go into the laboratory? And so what I'm suggesting is that we think about the laboratory more. We think about basics. What are the basics? Well, our fundamental mathematical entities are binary bits, as we all know. It's a decision. Is it true or is it not true? If we're going to measure the width of the room, what we would do is we would say, okay, we're going to use meters. Will a 16-meter stick fit across this room? No, we put a 0 down. Will an 8-meter stick fit? No, it won't. We put another 0. Will a 4-meter stick, and we're going in powers of 2? Yes, it will. So we lay it out, mark the end, and then we look at the remaining. We say, will a 2-meter stick fit? So we get a series of binary digits until we're down to some point, and we don't know. These are the quanta, these ones and zeros of Shannon information. And as you know from simple computer courses, that ones and zeros total up to give you the total amount of information in the system. These represent the lowest level of decisions that we can make in measuring length or time. But there is something that's lower than that. The fundamental methodology of combining these is in Boolean logic, with our truth tables and, or, not, and so forth. So my question is there a way to go beneath or inside the ones and the zeros? And I suggest that we do that, and we do it in a way that articulates a well-defined mathematical structure. Otherwise, we have a set of ad hoc rules now, and so if we can't do that, we're not getting anywhere. If we just use probabilities, the probabilities don't close. They're just numbers. I mean, what do? We multiply them together and we get other numbers. It doesn't form a system that's cohesive in the way that I'm going to describe. I'm going to propose, and this is really, this sentence right here is the other half of my talk, other than that one-to-one correspondence for the networks. I propose that we use the two-dimensional representation of the Markov monoid as our fundamental entity for logic. And we make the interpretation that if we have a 1 and a 0, that represents a 1. And if we have a 0 and a 1, it represents a 0. And we can have any pair of probabilities that add up to logic between the two. You say, well, in that we're just looking at probability. No, we're looking at a pair of these. And you'll see as this progresses why this is a little bit different. We know that independent probabilities multiply, so we need to combine these objects. We need to take two of these and multiply them in some way. That gives another object and we get closure. I'm going to call these, you know what a spinor is. A spinor is not just a pair of numbers. It's not a vector. In fact, it's a representation of the unitary group. This is a representation of the Markov group. It is not a vector, but it is a pair of numbers, and they are non-negative, and they sum to 1. And that's the definition of what we mean by it. And I call this bit vector, rather than saying bit vector, representation of this monoid, I call it a bitter. So this representation space, and it could be n-dimensional, but I'm going to concentrate here on 2 dimensions. Neither a spinor or a bitter is a vector. It's an ordered pair of non-negative reals that sum to unity. That's what a bitter is. Now, we've got to get closure, and we've got to combine these things. So we've got to be able to multiply these things because they have to generalize Boolean logic. So we have to get back to and, or, not, nor, and so forth like that. So we have to take a product out of them and get a third one. So x, a bitter x times a bitter y has to give a bitter z. Well, this is going to give us a set of coefficients here. They're not structure constants. It's not a cross product. It's a new type of product. They're actually going to be alpha different types of products, and I'll show you that. And this is an indexing that goes 0 and 1. So I, j, and k go 0 and 1. And we use the summation convention over repeated indices. Index alpha is going to range over all the different logical combinations that we can have, like and, or, not, nor, and so forth. This C must give closure, and if x and y are bitters, then Z must be a bitter. How do we define that? Well, it turns out that if you look at the products that you have between x and y, there are 4 objects that you form over the indices. And those exactly cover all these possibilities of true, 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 false, and so forth. And so, it follows that the 2 components of Z must be the partitions of these 4 objects into 2 categories. Because the sum of those 4 probabilities, those joint probabilities, exactly sums to 1. So if I put some of them in the top bitter for Z and some of them in the bottom, then I exactly get a sum of 1, and they're always non-negative, so I get a closure for a mathematical system. How many ways can I do that? I can do that in exactly 16 ways, partitioning 4 things, and I come up with a code for that. I use the fact that I have, for example, which one of those 4, I really mean a 1, 0, 0, 0 would mean I take the first one to be in Z1 and the rest of them not to be in Z1, they're in Z0. And this, of course, is an AND operation because it says it's the probability that X is true and Y is true at the same time. This would give the probability that Z is true. So this gives us an AND. And it's one of the decompositions. So alpha is equal to this binary thing for the AND operation. You can quickly see, I don't have to go through a bunch of stuff here to convince you, that you do get 16 possible operations. 2 are kind of trite. One is always true and one is always false. You say, is there a linear combination? It's a product. But we have more than a product. We actually have 16 products. Do we have a linear combination? Can I add 2 of these things together? Can I take alpha times 1 plus beta times another one and end up with a bitter? And the answer is no, you can't, not generally. However, there's a restriction, and it's an if and only if, necessary and sufficient conditions, is if the coefficients form a representation of the Markov monoid, meaning they sum to 1 and they're all non-negative, then in fact the combinations of those bitters will exactly be another bitter. So there is a type of linear combination, and it's done with those coefficients. And it turns out that gives you a weighted average. It's kind of like people voting on things. And so it makes sense in the sense of probability theory. So now we have a new mathematical structure with these bitters as the entities. We have 16 independent products and 1 type of linear combination And to the best of my knowledge, I know nothing about this existing in the literature. And at the same time, you can still do continuous Lie transformations on these bitter spaces. So, I mean, these are rather complex objects, and what we have done is we have, and it's not unknown in mathematics. If you take something like a linear vector space, that's a well-defined mathematical structure, and then you say, oh, and now we want to do something else on that. What else do you want to do? You want to define a scalar product, and that makes it into a metric space. Or you want to define a commutator, and that makes it into a Lie algebra. So whether the linear vector space goes to become a Lie algebra, or whether this linear vector space becomes a metric space, depends upon what additionally I do to it. Well, here we have representations of the Markov monoid, and now we're adding another richness layer onto that. In regular Boolean logic, I might point out that the NAND operation is sufficient to build all other operations in computer systems. And that's not true here, it turns out. And now I want to talk about a new kind of number. And the number I want to suggest to you is that the numbers that we use in these binary decisions are these bitters, and they're in these pairs, 1, 0, 1, 0. Yes, we could put the meter stick there. Yes, we could put it there. Point. No, we couldn't put this one here. And here's an 80% chance that we could and a 20% chance that we couldn't. And then from here on, we don't know. Half and half. I don't know whether it fit or not. So we have complete lack of knowledge there. And we could summarize that with our normal binary number pretty much like this. We could say, use only the upper parts, a 1 and a 1 and a 0, and then, of course, a 0.8. So the numbers begin to look a little bit different. But we have a structure underneath that for logic that will allow us to define exactly the multiplication, division, addition, and subtraction based exactly on the rules of Boolean logic extended to this system. I mean, there's no question of how to do it, but that would be a lecture in itself, and everybody would be asleep. It turns out that these bitter numbers, since they include the binaries, include all past number systems, Boolean logic and arithmetic, in the limiting cases where they're 1 and 0s. In other words, products of these group representations contain the reals, the rationals, the complexes, anything else you want to form, and this logic that's continuous contains all of the Boolean logic also. You can say, okay, well, okay, so we've got some fuzzy numbers we can deal with, and maybe they're good for representing the width of a room a little bit more accurately and tracking the information flow as we put it into computers, and maybe it's practical. Well, I think it will be practical, because if we had computers that could manage uncertainty, and that was my original objective in all of this, and do it accurately with a well-defined foundation, then in fact in our engineering tables and all of our operations, we would know what's the temperature outside, what's the thermal conductivity, what's the this, that, and the other, and all of those numbers, when they're folded together to build a bridge or to build a skyscraper, would automatically give us the error tolerances, and we wouldn't have to program them explicitly. We could program them now, but it's enormously difficult, especially for all kinds of decision making, financial decision, and so forth.
You assume here that all these measurements or values are independent.
Yes, I do have to assume
In
that.
real life, it's not correct. Therefore, in other case, everything.
You have to assume that each of these measurements is independent of one another. Yes, that is correct. And that's a strong assumption. One can define these two-component bitters as objects and then overload your logic operations. So now you can say, I've got all these things. Their numbers are now group representations. And I can try to say, well, how do I deal with the computers? Well, I can try to overload that, but you really need to kind of rebuild everything. And so the situation is very complex, and the most complex part comes in the following. The foundation of our computer systems is when we get to a place and we say, if x is greater than y, then do this, else do this. That's the foundation of everything. But here, there's a certain probability that x is greater than y, and a probability that it's not, if these numbers are both bitters, or even one of them. So then it follows that you really need to do both things, unless you just take the most probable path. So what you really need to do in the computers now is to spawn threads at every decision point. Each thread carrying the probability that that process is the valid process. You know, am I taller than Gary Blampied? Well, I mean, if you stand us up, we're pretty close, and maybe 80% of you say I'm taller, and 20% say he's taller. Now, if we had an algorithm that split, we'd really need to consider the fact that maybe he is taller and explore all of that. Well, now this is like creation and annihilation operators in physics. We're constantly creating these new threads, and of course, in a loop process, you're going to create trillions and trillions of them. They have to die somehow. So below a certain threshold, we have to annihilate these processes. Really need to rebuild your C++ and Java. I don't know how to do that. The foundation of logical decisions gives us a true paradigm shift with these various branches that are spawned. But now we can follow the actual information content as that content is lost in various mathematical operations. So when we add two numbers, we lose information, as you know, just like adding two links or multiplying two numbers. So through all of our mathematical operations, it's almost like a physical process where we're losing information that's irretrievable, and we really don't know how to get it back again. Our information content is normally measured in Shannon's information as the log base 2 of the probability. But if we have a bidder, we can say, how do we define our information on that? Well, we could impose the boundary condition that if I have a 1-0, I get 1 bit of information, or 0-1, I get 1 bit, because both of those are a 1 or a 0. And if I have a half and a half, I get no information. And if I put that in as a boundary condition, and look at this equation here, where I look at A times the first probability to a power plus B, the second to a power, and try to determine A and B, it turns out it's unique. Of all of the different Rayleigh entropies that it could give, it gives, it turns out, the second order Rayleigh entropy, which says that the coefficient here has to be 2, and these powers have to be 2. And basically that says a smooth transition to the Shannon entropy out of these bidders is measured when I don't really have a 1 or a 0, but I have some probabilities, is measured this way in an optimal sense. For example, if you knew that it rained 50% of the days in Columbia, South Carolina, and the weatherman said, it'll rain tomorrow, he gave you 1 bit. He said, it won't rain tomorrow, he gave you 1 bit of information. If he says 50-50 chance, then he didn't tell you anything. But how much information did he give you if he said there's an 81% chance of rain? And what I submit to you is the smoothest transition to that definition of information is you take 2 times 0.8 squared plus 0.2 squared, and that gives you a measure of information that smoothly interpolates between those two values. There are many people in physics that think you should use the Shannon definition that's weighted as an ensemble, which means you write p times the log base 2 of p. And if you plot these two functions on top of one another, they're almost exactly coincident. But of course they are different. And that ensemble definition cannot be used as a definition of entropy. And there's a good reason for it. It's not additive. It is an ensemble definition, and it is close to this one, because it's almost imperceptible if I look at the curves plotted one upon the other one. In general, it turns out that the extrapolation to n dimensions is I have n times the sum of xi squared, and we can show that that's a smooth generalization. And now using that, and again, you have to assume the independence of these components, and that is a strong assumption for the various independent processes. If you don't assume that, you're mired down forever in joint probabilities, and you're just lost there, because it's very difficult to know how those things are dependent upon one another. But here we have the tools to track the loss of information through all logical and other types of processes. It's our proposal that bidder-based numbers be used as a foundational number system to generalize the reals and to utilize it there. It includes the real, so we haven't thrown anything away or lost it. For observations and for computation, and remember that this is a generalization of the number system, so you get everything back if you want it. It allows for the automated management of uncertainty and error in scientific and engineering applications. It'll provide this multi-threaded computation, and I view this kind of like a Feynman path